So, well, welcome everyone to this week's Durham Geometry and Topology seminar. So it's a pleasure to have Christine Breiner from Fordham University. And she's going to talk about harmonic maps into CAD-K spaces.
Thank you, Fernando. Thanks for the invitation. It's nice to see some familiar faces. And I have to say that, this pandemic sucks, but I can accept a lot more talk invitations than I could have otherwise. So it's a pleasure to be here with you virtually. Today, I want to talk about some very recent work with Chica Messi at Hopkins, and she actually is an expert in these CAD0 spaces, in non-positively curved spaces, and using harmonic maps into non-positively curved spaces. And I had studied harmonic and biharmonic maps using PDEs, and we did some work together that sort of crossed over between the two. And there's some of this work I'll discuss is joint with a number of people. And then the most recent work is with Chica. So I will start with some very sort of basic reminders. I'll mention harmonic maps in Riemannian manifolds, and then I will leave it behind because we're not really going to deal with that. So we're going to be starting with some map between two geometric spaces. They can be Riemannian manifolds, they can be metric measure spaces, they can be metric spaces. And we need to have a notion of energy. And so the energy is sort of intuitively what we want to think about is measuring the stretch or the dilation of the map at each point in the domain, and then integrating this quantity. So when we're thinking about energy, that's what we're thinking about. Sorry if you hear small children in the background. So a harmonic map, if we have two Riemannian manifolds, this is probably well known to most of you, we define the energy up to a 1/2 to be the integral of the norm du squared over the domain. And du here is the differential. And if you want to know in local coordinates what it looks like, or a reminder of what it looks like, this is what you're doing in local coordinates. Again, we won't need that at all. That's just to remind us what we have in the smooth setting. And then when you have these two Riemannian manifolds, we're going to call a map harmonic if it's critical, if it's an actual critical point for the energy functional. And the next thing I'm going to put up, sometimes some people don't need this at all. Some people haven't looked at a calculus of variation problem in 20 years. So what we mean by that, and what do we mean by critical? We actually mean the calculus of variations definition. So in the Euclidean setting, what this would mean is you have compactly supported functions with finite energy, and then you're just looking at the difference quotient of the energies as t goes to 0, and that should be 0 if the map U is harmonic. From this, if you're in the manifold setting, you get from this the Euler-Lagrange equation given below. So this gives you this is, I guess, in the manifold setting, I should say. Of course, if you're in the Euclidean setting, the Christoffel symbols are 0, and you just get the harmonic maps are harmonic functions. The coordinate functions are harmonic. Okay, but this is in the manifold setting. You have a PDE. Is the point I want to remind everyone. You have this PDE. Sometimes the map only satisfies this weakly, right? It's not satisfying it point-wise, but you satisfy this weakly, and so there's a whole nother story, right? You could have finite energy and not even be continuous. There's a whole nother story when you're dealing with maps into manifolds, but we're not dealing with that in this setting. We won't have a PDE. And so I'm going to leave that part of the story here. And I'll get to the stuff we're dealing with as quickly as I can. Just a reminder, in the smooth setting, we have lots of examples of harmonic maps. They appear everywhere. Okay, so we have harmonic functions, we have geodesics, which of course are critical for the length functional, isometries, totally geodesic maps. Minimal surfaces are special in that that conformal maps are harmonic if and only if they're minimal. And then holomorphic maps between Kähler manifolds. So there's lots of examples that we have in the smooth setting. Okay, but today we're going to consider maps where we have only maps from Riemann surfaces into compact locally cat-kappa spaces. And so I want to talk briefly about what these are to make sure that everybody has some sense of what the target is. So for us, I should point out also the kappa here we want the kappa to be greater than 0, strictly greater than 0. So you should be thinking about things like spheres, basically. So we're allowed to have positive kappa. And so what is this cat kappa space? So a cat kappa space, first, it's a geodesic space. It's a metric space that's a geodesic space. And the kappa is giving us is telling us we're trying to generalize the notion of sectional curvature bounded above. And so this is telling us that we should compare or think about this as a manifold with sectional curvature bounds above by some kappa. Okay, so that's sort of the in the smooth setting, that's what we would get with this definition if we had a smooth manifold. But we define this sectional curvature via comparison triangles. So what you do, let me draw a little picture here. So you take 3 points, and because kappa is positive, we have to have sufficiently small triangles depending on the kappa. But you take some geodesic triangle in your metric space, and then you take the model space, which for us, because kappa is greater than 0, the model space will be a sphere of radius 1 over root kappa. So we're going to take the S2 with curvature, with sectional curvature equal to kappa, right? So it's the radius 1 over root kappa. Okay, so we have this, that's our model space. And then we take another triangle here, a comparison triangle here that has the same side lengths, P prime, Q prime, R prime. So they have this, it's another geodesic triangle with the same side lengths. And then you just do a comparison. Oops, I had white here. You do a comparison. So here's some curve of length L, and you've gone some distance along PR. So you go a comparable distance here, and you look at this guy, L prime, and L should be less than or equal to L prime. So people say, often they say, triangles in cat kappa space are thinner than triangles in the model space, the sphere of with curvature kappa, with sectional curvature kappa. So really, but what you're thinking about, we have some kind of upper curvature bound in what they call the Alexandrov sense. So imagine it's like an upper curvature bound. And if you're kind of trying to figure out what we're really after, just think about spheres, and that's okay. Spheres without a Riemannian metric, spheres that are just metric spaces. Okay, so we want to talk about harmonic maps in this setting, so we need to know what kind of energy we're using. And there are a few definitions of energy out there for, there are a few definitions of Sobolev spaces out there. We're going to use the one that was defined to understand harmonic maps. So that it was given to us, I think, in '93 by Korevaar and Schoen. So Korevaar and Schoen were studying geometric rigidity problems using harmonic maps into non-positively curved. So cat 0, they were looking at spaces. So they define energy by the first thing they do here. Maybe I'll use purple. Is, you start with a map. We're going to be confining ourselves to C. I'm going to give the simplest definition. There's a much more broad definition of the energy, but we're only looking at Riemann surfaces into these cat kappa spaces. So I'll just always think about being in local coordinates in a domain in C. Okay. So you start with a map that's in L2 from this domain in C to X, and we're going to define these sort of approximate energy density functions. And this is given by averaging the displacement. So, oops, well, that's nice, but you average the displacement over the sphere of radius epsilon about the point Z. So you fix a point Z, you average the displacement over that. And the nice thing, so there you have these symmetric neighborhoods as epsilon tends to 0. If you're in the case where X is just the real line, then you get back the norm of the gradient squared, norm grad U squared. Okay, so it corresponds to what you should get if your target were the reals. So this is how we start, and then they define energy by looking at these linear functionals. So you think of this epsilon energy density measure. You have this epsilon energy density measure, and you define a linear functional with it. And so if the energy for a map is finite, then you have a bounded linear functional, right? And so Riesz representation theorem tells you that there exists some measure such that this guy converges weakly to that measure. Okay, so there's some measure that these guys converge to as epsilon tends to 0. But the nice thing is that this measure is also absolutely continuous with respect to Lebesgue measure. And so you don't just get a measure, you actually get an L1 function. So this E epsilon U you can think of as converging to this L1 function EU, which is, this is going to be our energy density function. Right, I mean, roughly you can think of this EU of Z is equal to norm grad U squared of Z, or I guess du squared of Z is what I was writing earlier. Okay, so now we have a notion of energy. The point here, of course, is we cannot get a PDE out of this. Like, there's no hope of getting a PDE, although you can get a lot of weak differential inequalities once we're going to define what harmonicity means. So for us, harmonicity simply means locally energy minimizing. That's the only thing we can do. We can't do better than that. Okay, so locally energy minimizing actually is great, because so this means we're minimizing with respect to domain variations, so diffeomorphisms of the domain, and target variation, so variations of the map. And this gives us a lot to work with, because we can get these weak differential inequalities out of it that mimic some things that you see for harmonic maps into for locally minimizing harmonic maps into manifolds. So so that's kind of why we like this definition. So why do we care about the problem that we're going to look at? We're going to be motivated by sort of two things. One is actually something we did, and one is something that in a pipe dream one would hope to do someday. And I very much am not claiming that we're close so to the second one. So the first motivation is just uniformization theorems. So we're going to prove a uniformization theorem using harmonic maps into cat kappa space, where kappa is greater than 0. So a uniformization for cat kappa spheres in particular. So the uniformization theorem for Riemann surfaces, this is well known. If we have a simply connected Riemann surface, we're conformally equivalent to the open disk complex plane or the Riemann sphere. And then, if you have a smooth Riemannian metric G and you're defined on some closed surface S, then you can show that you're conformally equivalent to a metric of constant Gauss sectional curvature. So that's our first motivation. And another motivation I'd like to point out is that there's sort of a non-smooth motivation, which I think fits a little bit even more so with the kind of result that we get. So this is a result that Mori proved and then Alfers and Bears proved separately later, I believe by quite different methods. So the idea is you start with an L infinity function. You just have this L infinity function from C to C, and it has L infinity bound strictly greater than 1. And so when I say unique, I mean up to the obvious fixing of points. So there's a unique homeomorphism of F taking C to C that satisfies this equation. So F is, you fix where F of 0 and F of 1 go, and then it's unique. Satisfying this equation, the Z bar derivative of F is equal to mu times the Z derivative of F. And I think of this, I'm going to talk about this later, as kind of an analytic distortion. Okay. And then something that can be shown pretty quickly is that if you look at the dilatation of F at each point Z, it's given by this equation H. So H of Z is 1 plus the norm of mu divided by 1 minus the norm of mu. And I think of this, the way it's, because it's talking about dilatation, as sort of a geometric or metric measure of distortion. So what this actually means, this dilatation means what probably you would think it would mean. So you have a circle at the point Z, and as you look at infinitesimal circles, these infinitesimal circles are mapping to infinitesimal ellipses. Okay, and the ratio of these axes of the ellipse is actually equal to H. So this is F of Z here. Okay, so this is how, or this is kind of what we want to be thinking about, is we're trying to understand maps into our maps into our kappa space, which satisfies some kind of analytic distortion control and geometric sort of metric distortion control. So I'll point out, of course, when mu is 0, you get a conformal map or an almost conformal, you get a holomorphic map. So you get an almost conformal map, F, and the dilatation is 1. So you get in the metric space sense, you get a 1 quasi-conformal map, if you know those definitions. It takes infinitesimal circles to infinitesimal circles at every point. Okay. So we're not the first people to do uniformization in this non-smooth setting for metric spaces. There's some other results here. So Reshetniak proved, I believe, the first one. He did sort of like approximations by planes, linear approximations for to get uniformization on simply connected domains. Bonk and Kleiner proved something that, if you have Alfors2 regular and linear locally contractible, then you have a quasi-symmetry with the sphere. So some conditions on a sphere give you a quasi-symmetric, which is somewhat related to quasi-conformal. And then recently, there's 2 newer results, Rajala and Lechek-Wenger, prove results that are somewhat similar to ours, but in a completely different way. So I want to point out sort of what we are going to do at this point. So we're going to use 2 things to get at a uniformization theorem. So we're going to use a global existence result. So we're going to show that there is a harmonic map from the from the Riemann sphere into a kappa space that's not necessarily a homeomorphism, but then we're going to show that leads us to a homeomorphism via a branch covering result. So we're going to have a harmonic map that's not necessarily a homeomorphism, not necessarily even degree 1, okay, in particular, because, if it were degree 1, we could show right away it's a homeomorphism, okay, to show the following. So if you have a locally kappa sphere, so if you have something that is homeomorphic to the kappa sphere, then there's a harmonic homeomorphism. So then you can find a harmonic homeomorphism, which satisfies 2 things. First, it's almost conformal. And what we mean by that is in the Korevaar-Schoen notion of conformality and almost conformality, they define directional energy densities. And then you can talk about, you can get an inner product structure on the target by doing some pullback work there. So you define sort of a pullback inner product to talk about almost conformality of this map. And we show that it's 1 quasi-conformal. Okay, so we show 2 things. We show really, that's why I think I like the Mori and the Alfors-Bears result, because it gives us a sense of what we're trying to do. We're trying to do like the best sort of analytic comparison we can do to the smooth setting. And then we get this sort of metric geometric notion as well. So we get both ways of control. And it's the best control you could hope for, right? It's almost conformal and 1 quasi-conformal. That's the best control on the distortion you could get. So the bigger motivation, and part of the reason I think there was maybe such a gap between some of these results, is that the bigger motivation is the Cannon conjecture. And let me issue my disclaimer: I am not an expert in geometric group theory, so let's make that clear. But there is a way to think about. There are many framings of the Cannon conjecture, and one of them makes it clear that really you can be thinking about kind of uniformization theorems in some sense. So this is maybe on this slide is what maybe the geometric group theorist would say, and then on the next slide I'll relate it to the maps we're interested in. So the conjecture says that if you have an infinite finitely presented group and the Cayley graph is Gromov hyperbolic and the space at infinity is homeomorphic to the 2 sphere, so there we've got something homeomorphic to the 2 sphere, then G is Kleinian. So G admits the discrete co-compact action, isometric action on H3. Now, why did Cannon care about this? That's part of the reason I think there's a gap in the literature. Cannon cared about this because he wanted to understand, how do you take an object that has varying negative curvature and promote it to having constant negative curvature? And the reason, in part, that he wanted to do that was because he wanted to deal with the Gromov hyperbolic portion of Thurston's geometrization. Okay, and of course, in the early 2000s, the geometrization conjecture was solved, but Cannon's conjecture is not proven through the geometrization. So it's still open, actually. It's still an open conjecture. And I think I had to double check in my abstract. I said, our work relates to that. And no way are we claiming we've proven this, right? But how does it relate? So how could it possibly relate? The way it relates is what you see on this slide. So I believe Dennis Sullivan had framed it. So he pointed out, if you have the same hypotheses, then if you could show that this boundary, which was homeomorphic to S2, was actually quasi-symmetric to S2, then you could prove Cannon's conjecture. And quasi-symmetry is a measure of distortion. It's weaker than Lipschitz. It's actually, if you think about quasi-conformal and quasi-symmetric is more of a global measure of the distortion. Quasi-conformal is an infinitesimal measure of distortion. In the smooth setting, they're equivalent. Once you have one, you have the other. In the metric space setting, they're not always equivalent. So you can have good control locally and not globally in this way. But what is how can we frame it? The question then really is, if you had a metric space that was homeomorphic to S2, if that's all it seems like it's completely out of reach at this point to try and show that metric space is quasi-symmetric to S2 or quasi-conformal or anything. So what conditions right now can we put on that metric so that we get a map with controlled distortion? So what kind of hypotheses can you add? And then what kind of conclusion can you get in terms of the controlling of this distortion? So this is what we, how it connects back to this sort of big open conjecture, again, that everybody can chip a little bit at it, but that's sort of how we're thinking about what we're trying to do. So we put the hypotheses of an upper curvature bound. So we have a metric space homeomorphic to S2, and we give it an upper curvature bound. And then we actually have to give another condition. We have to say it also is a surface. So that is a big hypothesis, because that's controlling the Hausdorff measure. There are examples up here where the Hausdorff measure of your boundary is something like 2+. It has Hausdorff dimension 2+ epsilon. So there are issues with this, but actually the previous works also can't deal with those cases. You have to have some kind of sort of control on the Hausdorff measure. So nobody's really been able to eliminate that. But then what the controlled distortion we get is very good, right? It's one quasi-conformal and almost conformal map. So we have to add a stronger hypothesis in some ways, but we get a very strong conclusion. So now I'm going to take you through a little bit how we do these two things. So the first thing, as I mentioned, there's a global existence result we have. And this was joint with a number of people. And it should remind you, for the experts in geometric analysis and harmonic maps, it should remind you of a very well-known result, the Sachs-Uhlenbeck result on the existence of minimal two spheres. So really what this result is, it's equivalent to the Sachs-Uhlenbeck result in the metric space setting. So we start with a compact Riemann surface, and we have a compact locally cat kappa space. So here we don't have any extra condition of the target being a surface. We just have a compact locally cat kappa space. So if you have a finite energy continuous map, so finite energy in the Korevaar-Schoen sense, then there's a dichotomy. So either there's a harmonic map that's homotopic to your starting map, or there's an almost conformal harmonic map from the two sphere. And this is commonly called a bubble, this V in the literature. And you might say, well, you have now an almost conformal harmonic map from the two sphere if X is the two sphere. So what are you missing? So, what's missing to just do a uniformization theorem at this point? So let me point out that even if phi is a homeomorphism, so, phi is taking S2 to really S2D, right? Something that's homeomorphic to S2, right? Even if we have a homeomorphism, there's no guarantee the bubble is even degree 1. Right? There's no guarantee that in the second case, in the first case, of course, you'd have at least a degree 1 harmonic map, but you don't know that you ended up with a homeomorphism. Although, if it's degree 1, you might think, well, if we want to have smaller energy, we would expect a degree 1 map to be a homeomorphism. But the bubbling actually can happen in a way so you end up with like a degree 2, degree -1, 2 different maps that are connect sum. And so V could be like a degree -1 map, which would be okay. Well, at least degree, it would have the absolute value of the degree would be 1, but it could be the degree 2 map. Like you could jump in degree. So actually when Chika and I, we got this result with people, and I knew the bubbling worked very well. But then the question was somehow like, well, why can't you get at least degree 1? Why can't you get a homeomorphism? Because once you have degree 1, again, you think you probably should be able to show it's a homeomorphism. So that's what we were really kind of interested in. So I'll talk maybe 2 minutes about how this work, how we got this work. So this global existence, as I said, generalizes Sachs-Uhlenbeck existence of minimal 2 spheres, but of course we don't have a PDE available. So it's a completely different strategy. And so really what we're doing is we have local convexity for ket kappa spaces. So you have, that lets you get convexity of the energy functional. So you can get Dirichlet solutions. So the existence of Dirichlet solutions. And then the regularity also comes from finding these weak differential inequalities that are, again, exploiting this convexity. And so you have existence and regularity of Dirichlet solutions. And so the way we do this problem is essentially think of it as a discrete harmonic map heat flow. Okay, so it's a harmonic replacement process, but it's really, if you know Birkhoff curve shortening, it's similar to that in style. Okay, and the way the bubbling happens is if in the replacement process, you have points where your, let's just say the Lipschitz bound is blowing up. So you have sort of pointwise Lipschitz bounds, you're losing control under the replacements. Okay, because you're replacing on these disks, you would have your domain, you'd have a number of disks. You'd start with your phi and you'd replace on maybe this disk and this disk, and then you'd replace next on this disk, and then you'd replace on this disk. And after you replace on all the disks in the cover, you look at your new map. The size of the disks on which you do the replacement depends on how big a ball in the target you can get your existence of your Dirichlet solution. And so as you're doing these replacements and you get new maps, if the Lipschitz bound starts to blow up, then the disks in the domain on which you're doing this replacement have to get smaller. The next round would be smaller and smaller. And so the bubble starts happening because you're doing replacement on smaller disks. And so what you do is you start blowing up the domain. And as you blow up the domain, you do the replacement on domains exhausting all of C. Okay, and then you get a harmonic map. They now have good control. You blow them up in a way so they have, you have equicontinuity. You don't converge to a constant. You have to find the middle ground there. So you end up with a harmonic map on all of C. And then you just have to show that there's a removable singularity theorem so that you can close it up to the sphere. So that's the dichotomy. Okay. So again, we could end up with something that's not even degree 1, even if we had a degree 1 map to start. Okay. So the way we get to our branch covering and then finding our homeomorphism is we do some local analysis. And really the idea is we want to understand what happens if you essentially have what amounts to a full rank differential for your map, or the equivalent of that. So we can't talk about derivatives of our map, so we have to define things via tangent maps. So we will say a harmonic map from a Riemann surface to a locally ket kappa space is non-degenerate if at every point infinitesimal circles map to infinitesimal ellipses. So what that's really saying is that if you look at your tangent maps, so harmonic maps into ket kappa spaces, we show they have tangent maps. If you look at any tangent map of U at that point, then if you look at an infinitesimal circle, you are not going to get, well, that doesn't look right. You're not going to get this kind of picture. You're not going to get, so no. So there's no collapse along rays. Okay, you have these homogeneous maps, homogeneous harmonic maps. And the point is you don't want to collapse along a ray. So it really is generalizing this notion of a full rank differential between manifolds. So we're going to be looking at these non-degenerate maps. And the big result that we prove that gets at the uniformization is that if we have a proper and non-degenerate harmonic map from a Riemann surface to a locally cat-kappa surface, then you actually have a branched cover. So this is, once we have the branched cover, then we're almost done. So the main work is to get this theorem. This is the big part of the work. So how do we get at having a branched cover? So I'm going to point out the things we would need to show to understand that, and then I'll give the finer details. So the first thing you need to show that we get at least a local homeomorphism away from some set is we're going to use the following result. So I'll write it over here to start. So we need to show first the map is discrete, and then we'll show the map is open. And then we can use sort of classical work of Väisälä to show that actually the map is a local homeomorphism away from a set B, which is not necessarily discrete, but has topological dimension 0. So that doesn't really help us. We have to do better. We need to show that that set is discrete. But at least we know we're a local homeomorphism away from some set. And then we're going to look at that set. So how do we get the map as discrete? This part, actually, you don't need a surface. You just need a locally cat-kappa space and a harmonic map. So this comes from the fact that we have a harmonic map and then the non-degeneracy. So this is enough to imply the map is discrete. The idea being that if the map were not discrete, you look at the tangent map or a tangent map. And if the map were not discrete, you would actually have collapse along a ray at the point where your points are converging. So that's where that comes from. That's not a difficult argument. The harder thing to figure out, and the reason we wound up having to add the hypothesis of surface, was to get that the map is open. Okay, so to get that the map is open, we actually use a characterization of what are called the Alexandrov tangent maps. Okay, and so this shows the map is open. So once we can find a way to characterize the Alexandrov tangent maps for I guess I should say also non-degenerate, we need them to be non-degenerate, because if they weren't, we'd end up with the collapse along array as our characterization. So this is a different notion of tangent map. And this is where we actually had to use the surface hypothesis. So I'll say a few things about that on the next few slides. So that's sort of the main setup. Now, how do we get so now how do we go from here? We need to show B is discrete. So how we get from here, so we have to go from there over here, we have to still show that B is discrete. And this actually comes from the fact that we have an order function. Some of you might know of it as the frequency function. And we're able to show, so this is order function / frequency function. We're able to show that that points with high order are discrete, and that the branch set is contained only when points with high order. So order bigger than or equal to 2. Points with order 2 or higher are discrete. So this is like, think of it as if you don't know the order function, the frequency function, think of it in the smooth setting, it tells you the order of vanishing at a point. So we have a way of talking about the order of these maps at each point. And so we get it that way. And what we have to do is look at this characterization of Alexandrov tangent maps show how it relates to both the order and the winding number. So we have to figure out how we can pick up a winding number, which is really a local degree, right? The local degree at a point. So we're relating all of these things using the fact that we have a harmonic map, the fact that we have tangent maps, and then the fact that we have this notion of an Alexandrov tangent map. Okay, so got about 15 minutes, that's perfect. Okay, so let me say a few things here. So what are these Alexandrov tangent maps? So the nice thing about Alexandrov tangent maps is they all map into the same space. So I'm going to tell you the space they map into, and then I'll tell you sort of what we show about them. So if we're given just a geodesic space, we can define the Alexandrov tangent cone as the cone over the space of directions. So this script E sub q is just the space of directions at a point Q. So we actually take the cone over the space of directions, and this is what we call our Alexandrov tangent cone. So metric spaces with curvature bounded below, you can show that the Alexandrov tangent cone and the Gromov-Hausdorff limit, pointed Gromov-Hausdorff limit of the metric space agree. And so you can show that, you know, Alexandrov tangent cones are cones over curves, you would expect if the in that side, you can show it with curvature bounded below, you have some control on how Alexandrov tangent cones behave. With curvature bounded above, they can be quite weird. But when you add the condition of a surface, you get, again, you think of these Alexandrov tangent cones, they're really Gromov-Hausdorff limits, pointed Gromov-Hausdorff limits of your metric space. So that's where we use the surface condition also there. So what is an Alexandrov tangent map? So I do not want to define a tangent map because it's very involved in this case. But I'm going to tell you that if you had a tangent map for you, then you construct an Alexandrov tangent map from the limits of the tangent maps for you. So the idea is, I did it again, sorry. You have your harmonic map. You have this log map that takes, for any measure you put on your metric space, the log map takes it into the tangent cone with that measure given on the previous slide by this method. So you take the measure in X, the metric in X, you take the distance between Q, which is going to become our cone point, and some Q prime. And then you look at the angle made by the geodesic in the equivalence class of the space of directions. Okay, so the log map maps you into the tangent cone. So if you had maps that converge to a tangent map of U, then these maps, you take those maps U sigma, then you map them into the Alexandrov tangent cone. They also have a limit, and we call that limit the Alexandrov tangent map of U. And so why do we care? Why would we even think about doing this? Because tangent maps into metric spaces, the metric space is some very abstract space. We have no idea what it looks like, actually. We know it's non-positively curved. That's the only thing we know. But if you map into these Alexandrov tangent cones, you know explicitly what the metric space looks like. Okay, you know what they're mapping into, and so you can do some work with it. So I should say, what's the key points here? And in general, tangent cones don't need to be well behaved. And so we prove that if we have this is a cat kappa or locally cat kappa surface, then T sub Q of S is a metric cone over a finite length curve. I think this was known in the metric space community in different ways. Like they didn't necessarily put the surface condition, but there are other conditions you can put also. So we had the surface condition because we needed it in a few places. The other thing is that's the more important one for our purposes is that if you have an Alexandrov tangent map of a harmonic map, that map doesn't need to be harmonic, actually. It's just some homogeneous map. It's not known that it's harmonic. And so the point here is that if U is taking sigma to XD, so now and XD is a locally cat kappa manifold. We don't even need a surface here, but we need a manifold. Then every Alexandrov tangent map is not only homogeneous, homogeneous, but it's also a harmonic map. So when you add the condition of manifold, you can show that the Alexandrov tangent map is not only a homogeneous map relating to your map U, but it's also a harmonic map. And the reason we need that is because we want to try and characterize these tangent maps to understand openness. And Korevaar actually characterized homogeneous harmonic maps from the complex plane into non-positively curved cones. So we're exactly in this setting. Okay, we put ourselves exactly in this setting. And when your initial map is non-degenerate, every tangent map, so this is, you can think of this as a Alexandrov tangent map, which actually has the same pullback distance as a tangent map. That's how we show their harmonic. Has one of two forms, either if it's non-degenerate, either it looks like a constant times z to the alpha over beta, so it looks like z to some power, or it has this form here, which is sort of, if you look at what this does, it kind of wiggles. It wiggles symmetrically around. The circles map to these sort of wiggling around the origin, these loops that wiggle symmetrically. And as k goes to 1, you're converging to that picture where you have a bunch of rays, okay, symmetrically placed rays. Okay, so that's what we're avoiding, is that picture. And because we know this characterization, proving openness follows from this directly. So that's how we get at it. So yeah, there is, Korevaar did characterize when k equals 1. What I should say here is that alpha is the order of U at, I guess, 0 in this case, where we're centering. And beta is about the curvature. So beta is here. Beta is the curvature. How the curvature concentrates at the origin. And k is what we call the stretch function. Okay. And all three of these are independent of the tangent map. So because tangent maps are not unique, we need things that are independent of the tangent map. So we relate this alpha over beta to the winding number. And that's what's going to let us get at the fact that the branch set is discrete. Okay, so I have about 7 minutes. All right, so let me give you the application and how we get from the branched cover result to our homeomorphism. So the first lemma is pretty straightforward. It's if you start with a non-trivial, almost conformal harmonic map from a Riemann surface to a locally cat-kappa surface, then the map is non-degenerate. And this is just looking at directional energy densities. It's not a difficult problem, but it's what you would expect. It's what you get in the smooth setting. Almost conformality gives you non-degeneracy. And so, if we knew we had a degree 1 harmonic map from the 2-sphere to a locally cat-kappa sphere, then we could show we had one quasi-conformal homeomorphism with one quasi-conformal inverse. So that's sort of the first theorem, that if we knew we had a degree 1 map, then we could get our result. So let me point out how that works. So, if you're taking U from S2 to SD is harmonic, right? The only harmonic maps you can have to be almost conformal. There's a notion of the Hopf differential. The Hopf differential is, again, a holomorphic function, and you can show the Hopf differential has to vanish because you have a finite energy map. Okay, so you have an almost conformal map. The lemma tells us that this is non-degenerate. Okay, because the map is degree 1, we know it's proper. We defined global degree, so it has to be proper. We have a non-degenerate proper map, so we get that we have a branched cover. And then we use degree theory to look, we compare essentially our local degree to our global degree. You show that every local degree has to have the same sign. And so if you had a point where you were a local homeomorphism and the map was 2 to 1, then your global degree wouldn't be 1. So or 3 to 1, I guess, would be the chance you'd have 2 that had local degree that were minus or plus 1 and 1 that had local degree minus 1, and you would add up to 1 in the global degree at that point. But the problem is that that every point in the domain has to have the same sign on its local degree. And so that we use degree theory here to get that it's a homeomorphism. Okay. And then you can get the one quasi-conformality from some relatively straightforward calculations on the almost conformal, on the Alexandrov tangent maps. And one nice thing I will say is that in the literature that I've seen for metric spaces on these quasi-conformal maps, it's very hard to calculate that constant in most cases. So we get the constant, we get the QC1 by a calculation, and that calculation is actually not very hard. Okay, so it's really looking at the tangent maps and understanding what the tangent maps do, and then you can get the calculation out of there. Okay, so let me finish with our final application and a brief picture on the next slide. So the application to uniformization is the following. If you have a locally cat-kappa sphere, then there is a map from the Riemann sphere that is an almost conformal harmonic homeomorphism. It and its inverse are one quasi-conformal. And then you get the expected things that you're unique up to Mobius transformation. And the energy, by our definition of energy with no 1/2 there, is twice the Hausdorff 2 measure of the metric space. So this is what you would expect to get for a harmonic homeomorphism in the smooth setting. So this is our sort of final application. And how we get it is the following 3 steps. So there's a finite energy map. We just use, so how do we get the existence of a finite energy map? That's just using the convex geometry of SD. Okay, so just using the local convexity, we can get a finite energy map. It's not too difficult. Once you have a finite energy map, you use Saxon-Uhlenbeck to get an almost conformal harmonic map from the 2 sphere. Then you use, so that's our global existence result. Then you use our local result or our branched covering result to show that that map is a branched cover. So you have this map, U taking S2 to SD, that's a harmonic, almost conformal, harmonic branched cover. Okay, and then from there, we're going to use that map to define an equivalence relation on our sphere so that we get a complex structure on the quotient space. So let me show you the picture here. Okay, so we'll have this mapping. U will map this way to our SD. Q will be defined by an equivalence relation. So we'll just say P is equivalent to Q if U of P equals U of Q. So a pretty straightforward equivalence relation. And we'll call this map here the identity map because it's essentially the identity map on a fundamental domain in the branch cover, so it's on one domain of U that maps to all of S, right? Minus the branch points. Sorry, I should back up. I said something not quite right there. This Q is defined for every point. We're able to show using pi that we can get a complex structure on Q to show that Q is actually the Riemann sphere. Okay, so we can show the identity map. This thing I'm calling ID is actually a homeomorphism. Okay, pi gives us the complex structure. And since the identity composed with pi equals U and U is harmonic, we're able to quickly show that the identity is harmonic on Q minus the projection of the branch points. But the branch points are discrete, so we can show that you can use removable singularity theorem to show that the identity is harmonic on Q. So then you end up with this harmonic map from Q, which we show as the Riemann sphere. It's easy to see the identity is a homeomorphism from its construction, and that's what gives us our map. So this picture looks a lot like the kind of picture you see when you're doing some factorization, maybe in the Osserman, Royden, and I'm forgetting one of the authors, Gulliver, Osserman, and Royden looked at branch points of harmonic maps in the smooth setting, and their equivalence relation is a little more complicated than ours, but we only need this in order to get the quotient space as a Riemann sphere and to get the result that we want. So Oh my goodness, it's 8:55. That's amazing. I talked much faster, I guess, than previous times I gave this talk because I usually skip slides, so I'm sorry. I hope I didn't talk too fast, but I'll stop.